Hello, this video is assuming you've already either in class or via a separate video had a look at not just the base cubic function graph, which is y equals x cubed, but also when you've got this kind of thing happening, when you've got multiple factors and how that changes the shape of the graph. So this is just a functionality one, really, just to show you example by example how one would go about graphing it. So let's start off with example 1 here. Pretty simple. It's already in factor form. Y equals x minus 1 times x plus 1 times x plus 2. So we've got effectively 3 y-intercepts, right? Sorry, x-intercepts, beg your pardon. X equals 1, x equals minus 1, x equals negative 2. So let's start off the usual way. X-intercept, let y equals 0. Therefore, x equals 1. This is from the null factor law. That's 1, 0. X equals negative 1. It's negative 1, 0. And x is equal to negative 2. Negative 2, 0. Second thing is working out the y-intercept. And to do that, we let x equal to 0. And when it's in factored form already, basically just ignore the x's and then multiply the numbers together. So you've got minus 1 times 1 is minus 1 times 2 is minus 2. So you've got y equals minus 2, 0, minus 2. Okay, so if I'm looking at the graph here, if you look at slide 2 for the graph, I'll just draw the axes in. So we've got like so, and I'll put little arrows on the end of them to be a good boy. So that's my x-axis, that's my y-axis. I've got a 0 at 1. And I've got another 0 at minus 1, so I'll just try and space it out fairly tidily. And then I've got another one at minus 2. And then I've got a y-intercept at minus 2. So there's all my critical points mapped out. The only thing I haven't mapped out are my turning points. And you need to know that in this particular area of maths, we are not going to worry about turning points. You can position them roughly between the x-intercepts, but you don't need to work out the specifics unless it's a GDC question, in which case you can use a GDC to figure it out. And after we've done a unit on calculus, you'll be right to do it then as well. Okay, so the only thing is left to do is to actually draw the graph. And the problem we have really is that we need to figure out, does the graph go like this? Or does the graph go like this? Now, you can see that if I do it that way, I'm going to miss the negative 2 there. So that gives us a bit of a sense, I suppose, of which direction it should be. But it's not always completely evident. So I want to get you used to looking at a thing called the dominant term. Now, you can look at dominant term in a fair degree of sophistication, but we're going to have a look at it in just a really simplistic way. One thing you might note is that when I'm drawing a cubic graph, and it works for the base graph as well as this one, that if I start down here, then I end up here, diagonally opposite. And if I start here, I'm going to end up diagonally opposite, the quadrant diagonally opposite. Just a reminder, this is quadrant 1, this is quadrant 2, this is quadrant 3, and quadrant 4. So we'll always start in one of these quadrants, and it will always end in one of these quadrants, and it's always diagonally opposite. So if it starts in Q3, it goes to Q1. If it starts in Q2, it goes to Q4. I say start, but of course it goes on forever, but in terms of the stuff that you can see. Okay, so if we can figure out just what's happening at the start, we can pretty much work out what's happening at the end. And this is where dominant term comes in. And dominant term is really just an extension of the idea of what is the value of A that we've used in quadratics. We know that if A is positive, then it's going to be a smiley graph, and if A is negative, it's going to be a frowny graph, concave up, concave down. Similar sort of idea. We have a look at the dominant term, which is going to be the biggest power of x, okay, the leading term. So the dominant term is going to be calculated by going x multiplied by x multiplied by x. So we've got x times x times x, so we end up with x cubed as being the dominant term. If we look at the sign, if we look at x cubed for a start, when we've got x cubed on the left here, if we've got x cubed on the left here, then x is going to be negative, and so x cubed is going to be negative. So x cubed is negative. If we look at the sign of x cubed, it'll tell us whether it's going to start here or here. So here, we've got x times x times x, which is x cubed. So when I go to the left here, a negative x value, I'm going to be left with a negative y value, which means the graph is going to have to start here. Okay, so because a is positive, x is going to be here. Now, if instead, I'm going to undo this in a second, so just keep this in mind. If I instead made, put a negative outside the bracket here, or if I made this one here 1 minus x instead of x plus 1, or something like that, if I multiply it out, I'll get x times x times x is x cubed. I'll just make it a bit more obvious. I'll go minus 2 like this. X times x is x cubed. Multiplied by minus 2 is minus 2x cubed, all right? So if this was minus 2x cubed, then when I get x cubed, I'm going to get a negative number. And when I multiply it by minus 2, I'm going to get a positive number, which means that it would start up here. Now, this is the dominant term. Okay, so looking at the dominant term is the dominant term is just x cubed. Therefore, we're going to start in quadrant 3. Or if you don't want to have a look, if you don't want to remember the quadrant positions, just do that. It's going to start there. Dominant term is x cubed. Therefore, it starts in the third quadrant. Okay, now that I know that little bit of information, I can start drawing. And again, just be as precise as you can. Feel free to move the page around as you're drawing it to make it as accurate as you can. What we don't know is where these turning points are. So we're just having a bit of a guess. Put arrows on the end of it, and you're basically done. Remembering that we don't have to work out turning points yet. Okay, I won't go through as in much detail for the next examples. Okay, I might do one more example and then split to a different video for the rest of it. Example 2, x cubed minus 4x squared minus 3x plus 18. Now the problem with this is that it's not in factor form yet. So we're going to have to get it into factor form. So we'll do it the usual way. We'll substitute in, we'll use the remainder theorem or the factor theorem to work out a common factor and then go from there. So if I just say let f of x equal y of equal y, then I can now start looking at f of 1, and I'm just trying to really quickly work out whether it's going to give me 0 or not. So I've got 1 minus 4 minus 3 plus 18. That's not equal to 0. So it's not a factor. Let's try f of negative 1. That's going to give me negative 1. And then I'm going to have minus 1 is minus 5. Minus 5, no, that's not going to give me 0 either. So that's not equal to 0. Just try and do it as fast as I can, really. Let's try f of 2. I'm going to have 2 cubed minus 4 times 2 squared minus 3 times 2 plus 18. Let me see, that's 8 minus 16 is negative 8. Negative 8 minus 6 is negative 14, so that doesn't work. That's not equal to 0. Let's try f of minus 2, and I get, minus 2 cubed minus 4 times minus 2 squared minus 3 times minus 2 plus 18, and hope this will work. Minus 2 cubed is negative 8. Minus 2 squared is 4. 4 times 4 is 16. So I've got minus 8 minus 16 is minus 24. And, oh, thank goodness, minus 3 times minus 2 is positive 6. So I've got minus 24 plus 6 is minus 18 plus 18 is equal to 0. Phew. Okay, so therefore, remember to change the sign. X plus 2 is a factor. Okay, so then I might just try and keep all the working out on this slide here, but I don't reckon I can, but let me give it a go. Okay, so what does that mean? If I now divide x plus 2 into the other polynomial, we should be able to figure something out. So what is it? 1, 2, 3, 4. So I'll need 3 spots. I've got x plus 2 here, and now I'm going to use box method, reverse box method, to figure things out. So this is x cubed. X times x squared is equals x cubed, which means this is plus 2x squared. I need minus 4x squared, so I'll need a minus 6x squared here to make it. I'm going to go through this quickly. You can pause and rewind as many times as you want to, but this is stuff that we did last term. That's going to give me, let me say, minus 6x will give me minus 6x squared, and so this will give me minus 12x here, and I'll need a positive 9x in order to get there, and so this will be plus 9 here, and 9 times 2 is 18, which is the last term here. So we're right. So we've got y, we've got y equals x plus 2 times by x squared minus 6x plus 9. And this looks like it might be a perfect square. I've got something squared here. I've got 9, which is 3 squared, and 3 2s are 6. So it does fit the pattern of a perfect square. And so I've got x plus 2, x minus 3, because it keeps the sign of the middle term, all squared. Okay, so now it's factorized. I can just use my usual thing. So the x-intercepts, there's only 2 of them in this case. We've got x equals negative 2, so it's a negative 2, 0. And we've got x is equal to 3, 3, 0. This is called a repeated factor. It's x minus 3 all squared, so it's x minus 3 times x minus 3. So it only represents one intercept. Okay, next thing is the y-intercept. Let x equal 0, and there's no need to belabor it too much. If we go back to our original equation here, these things will go, leaving me with 18. So I can just go straight to y is equal to 18, 0, 18. Cool. So I haven't done dominant term yet, but I'll do that over here, just with a little bit of room. There's my x and y axes. And I'll just do dominant term in the corner here, which sometimes you can just go dt for dominant term. If I have a look at it, the dominant term, because it's not in factor form, it's really easy to see, is x cubed. And so it's going to start down here. Alrighty, let's put in all the information and go from there. So we've got minus 2, 3, and 18 is our 3 key numbers. So we've got x equals minus 2. Oops, I'll do it in a different color. And we've got x is equal to 3, and it's a repeated factor. I wonder if you can remember what that means in terms of how that's going to affect our graph. And we've got an 18 here, which is going to be a bit out of scale, but we'll put it here. Okay, so I'm going to start in the third quadrant because that's what my dominant term tells me to do. So it helps me start, and then I'm just going to see it through. So I'm going to go like this, and then I'm going to go down to 3, and then I'm going to bounce. That's what a repeated term does. It makes it bounce. Now you can see that my graph here does not look pretty at all. It's not. It's sort of stretched around here. It's probably worth doing again. It's a good thing about doing it on my iPad is I can repeat it. And for all I know, it's probably more like that. So the turning point's probably on the left rather than the right because it seems to graph better, but I don't really know until I do some calculus in order to figure that out. Okay, so that's 2 examples for you. One of them is just if it's already in factor form, what do you do? And the second example is if it's not in factor form already, what do you do to get it into factor form? In the next video, I'll go through a couple more examples. All of these link back to exercise 6F in your textbook. Example 1 is like question 1, and example 2 is like question 2. Note that in the textbook it asks you to do a sign diagram. I haven't asked you to do a sign diagram because I don't think they're particularly useful at this stage.